Okay, so transaction states. See, from now our main topic starts of transaction. Okay, so what is a transaction state? It is telling us the current point during our transaction. Okay, like I can say there are five types of transaction states to be precise. First, active. Second, partially committed. Third, failed. Fourth, aborted. And fifth, committed. Okay. As their meanings are clear on their own. Active, it means the transaction is currently running. Partially committed, it means that the transaction is not fully committed but only partially committed till now. Failed, it means the transaction failed. Aborted, it means the transaction aborted. Like there's a difference between failed and aborted. In aborted, you return to your original state, okay? And in failed, the you want that the transaction must be rolled back to its original state, okay? So there is a difference. In aborted it happens, but in failed we want that to be happen, okay? In committed, the transaction is fully completed and the final state is consistent, and the final database is consistent, okay? We are only considering consistency here, like on the asset properties, but if all the asset properties are satisfied, then we get consistent database. So this is the system. These are the transaction state. Let me write here. So what is active? It is the initial state. Okay. And transaction must remain in this state while executing. So I can say it is a running state. Okay. Must remain in this state while it is executing the operations, sending data or anything. Okay. Now this was the first. What will be the second? Second will be partially committed. Okay. So I already said that partially committed is a transaction is partially committed. Like its name is clearing its own meaning. Okay. So I can say the state of the transaction is partially committed, as it is still possible that it may have to be aborted since actual output is temporarily residing in main memory and not to disk. Let me clear this. Okay. What we want, what consistency says that I want either not consistency but atomicity, like it should happen entirely or should not perform at all. Okay, so in partially committed state, we what we want that it has to be rolled back to its original state. Okay, because we don't want any partial thing to happen. I gave you an example of UPI payments. Okay, so this is a thing. If I write it here, after the final statement of the transaction has been executed, the state of transaction is partially committed, not fully committed. Okay, as it is still possible that it may have to be aborted because already this is partially, and if there occurs any failures. Okay, because it is currently partially committed. Okay. Since since the actual output may be still not sent fully. Okay, so I don't think I need to write that again. Okay, now what is fade? This is also a transaction state. What does it say? That after the discovery of transaction, that the transaction can no longer proceed because of some errors. The error could be anything, software, hardware. Okay, such a transaction must be rolled back. After we got to know that the transaction cannot proceed ahead because of hardware or software issues, such transaction must be rolled back to ensure atomicity. Okay, this was simple. Now there is two more states. Okay, aborted. So what is aborted? A transaction is said to be in aborted state when the transaction has been rolled back. As I said, that in aborted we reached to our original state, but in failed we want to reach our original state. Okay, and the database has been restored to its state prior to the start of the execution. Okay, so here we want database to be rolled back. Here the database has been rolled back to its state prior to the start of execution. Okay, now there is one more which is committed, which obviously you know that the transaction has been completed. Enters into committed state after successful completion of a transaction and final update to the database. Okay, so these were the 5 transaction state. I think I can write it more clearly. Okay, so yes, these were the transaction states. I have already talked about it. Now, why do we need transaction states? Obviously, because to flag a current, to flag the current position in the transaction. Like if a transaction is occurring, then we want to know its state at any time. That's why we use transaction states. Okay. Now we want to start our concurrent execution of transaction. Now what we want, concurrent execution of transaction. What is concurrent execution of transaction? Like I already gave you an example of booking tickets on IRCTC platform. Consider if there is not concurrent execution of transaction and only one transaction runs each time, then what will happen? If your friend is buying a ticket, then you will have to wait until he purchases the ticket. You cannot purchase two tickets at once. Okay. Concurrent execution of transaction enables this, that you can book two or more tickets at the same time. Okay. Now, why do we need concurrent execution? Because there were two more main reasons for this, that it leads to good database performance, as I said, also less waiting time. You may consider waiting time and not waiting time, but here we wrote waiting time. Waiting time. Okay. The wait on the database. Okay. Like if many people are waiting, they are in queue. Okay. They are in queue like structure. So the queue like structure increases the weight on the database. Now, second reason would be overlapping input output activity with CPU increases the throughput time and response time. Okay. Now, what does this mean? So first of all, what is a throughput time? So throughput time is nothing but time taken to complete whole process, and response time is nothing but time taken to respond with the query. Okay. So I don't think I need to explain those 2 points. I already said why do we want concurrent execution of transaction and what are the benefits of concurrent execution of transaction. Okay. But there are few problems that comes when we do concurrent execution of transaction. Those are also termed as concurrency problems in transaction. Okay. So I guess I can write here topic as concurrency. What are the problems due to concurrency? Okay. First, inconsistent database can happen. If we do not design the database to be more perfect, then inconsistency may occur. Sometimes it is also possible that even though individual transactions are satisfying the ACID properties, okay, individual transactions are satisfying the ACID properties even though the final states of systems will be inconsistent. Like ACID properties are satisfied, still you can get the inconsistent database. Okay, so this is a problem. Instead of writing second, this one problem explains both. Okay, inconsistency may occur. Now there are few types of concurrency problems in transaction. What are those few problems? First, dirty read problem. Second, unrepeatable read problem. Third, loss update problem. And fourth, phantom read problem. Okay. So these are the four problems. I will explain you each problem one by one. Okay. But first of all, understand and read these four problems. So also one thing we must focus on, like I should write here in note that each transaction has been told that they are unknown in the system. What does this mean? That each transaction has been told they are unknown in system. They are running single, not uh, each the one transaction do not know that other transaction are running, and other transactions do not cause any effect on one transaction. Okay, this is the whole thing. Let me explain each problem one by one. So what was first? Dirty read problem. This is also called, okay, read write problem. So to explain this, I think I need to show you some graph. Okay, just a second. Okay, so this is a table. From this table I can clearly make you understand about the dirty read problem or the read write problem. Okay, so understand the example, like taking a equals to 10. Okay, first of all, what T1 sees, T1 first read the problem, so it reads a equals to 10. Then again T1 writes on this a equals to 11. I think let's consider that T1 writes it 11. Write function does here n plus 1. Okay, then T2 comes and T2 reads a equals to 11. Okay, no problem here. But what happens that T2 commit a equals to 11 to the DB. Okay, now T1 aborts the function, aborts the program. So what should happen? What should have happened that after aborting, A must return to its original value, that is 10. But as T2 has already committed A, so this is not possible. Like even after aborting, A is still 11. This is the problem. What T1 wanted that it read, it write, but then it aborted. So T1 wants A to be 10, but due to the commit of T2, A will be 11. Okay, this was the problem. T1 wanted A to be 10, but now A is 11 at the end of program. This was the dirty read problem. Okay, now there is one more problem. There are three more problems, not one actually, which is unrepeatable read problem. Okay, so unrepeatable read problem. I need to bring another table to make you understand this. Okay, just a second. Okay, so this table will surely make you understand what I want to say about unrepeatable read problem. Okay, so again consider taking A equals to 10. In all the problems, you must consider an example. Okay, so first of all, what T1 does, T1 takes A equals to not reads a equals to 10, then T2 reads a equals to 10, but then T2 writes a equals to 11, then T1 again reads a equals to 11. Do you see the inconsistency here? That the same T1 is reading same value of A, but same A, but A has different values. This leads to inconsistency. So this is the unrepeatable read problem. Okay. Similarly, uh, let me show you all the examples on the problems with the help of a table. Okay, so what was the third problem? Last update problem. Just a second now, let me bring both the tables now. Okay, so again, last update problem you can understand using the same methods ever. These two problems are also can be understood using the same method as above two. Okay, problems or examples. Okay, so yes, these were the problems. Now talking about problems is not the thing. We must give the solution to each problem. So what is the solution? So the simple solution is scheduling. We must write a proper scheduling algorithm to solve each problem. We cannot just say that, okay, so problem is there, we don't have any solution. We cannot say. We must write a proper scheduling algorithm to schedule the task such that each problem can be avoided. And meanwhile, we also do our work efficiently, like the concurrency. What we wanted to do, concurrency. So we want to avoid each problem and also maintain the concurrency to maintain the consistency. Okay. There are few types of scheduling. Okay. So first of all, let's understand. Okay. Scheduling is nothing but more like context switching in OS. You may have studied operating systems. In operating systems, we have context switching. In DBMS, we have scheduling. Okay. Let me write some formal terms here. So formal definition. So you may also read and understand it. When two or more transaction executed together or one after another, then they can be bundled up into higher unit of execution, which is called schedule. Okay, this is the proper definition of schedule. So a schedule of and transactions which can be T1 to Tn, okay, is an ordering of the operations of the transaction. But one thing we must know, that order must not change. Okay, so this is the thing. This is not something which is hard. Okay, this is an easy thing. Now there are two types of scheduling, which is serial scheduling and non-serial scheduling. In serial scheduling, what we do is first of all we execute all the task of one transaction, then we run another transaction. Okay, this is simple serial scheduling. It is consistent. No problem is there in serial scheduling because first if you will read A and read again A together without delete A, then obviously it will maintain the consistency and you will get A. And then if we delete A, then we will not get the thing. Simple. Serial scheduling is always consistent. But non-serial is not. Non-serial is when you try to arrange something and then you get the then you get the consistency. Like read a, delete a, read a. Here it is inconsistent. We need to make it consistent. Similarly, in all these, we need to make them consistent using some properties. So this type of thing is done in non-serial scheduling. Also, why schedule not why we will not doing be serial scheduling every time? Because again, there will be no benefit of doing serial scheduling. What you are doing is simply uh, what I said, like booking a train of one person, then we can book the tickets of another person. So this is simple serial scheduling, and therefore it is not preferred. Okay. So next we will study about the serial non-serial scheduling. So before non-serial scheduling, I will say more proper to be scheduling. Okay, before non-serial scheduling, can we somehow uh, quantify or say that how many number of schedules that we can make from n transactions? Of course we can using maths. Okay, using permutation and combination. So what I am saying is that if we have n different transactions from T1 to Tn, okay, where each transaction contains n1, n2 to nm processes or nn, not nm, but nn processes, okay, then we can find the number of schedules by there is a mathematics formula attached to it, which is simply n1 plus n2 dot nn, taking the factorial of this and dividing it with n1 factorial, n2 factorial. I don't think I need to explain why we are doing this, okay? This is simply a mathematics formula to find the total number of schedules. And by this we can understand that there will be multiple different, like if n is very large, then millions of different schedules. Okay, so we need to have some strong algorithms by which we can find a perfect scheduling for our transactions. First of all, we must know that we do not have any method to prove that a schedule is consistent. But from the above discussion that we did, we understand that a serial schedule is always consistent. So if somehow we prove that a non-serial schedule will also have same effects as of serial schedule, then we get a proof that this particular non-serial schedule will also be consistent. Okay. For a concurrent schedule to result in consistency, it should be equivalent to a serial schedule. Okay, and this is also called serializable. So we can uh, what I say, divide the scheduling based on two things: serializability and recoverability. Okay, so let me write it here so you can better understand. These are actually memorizing things. Okay, so we can divide the scheduling based on two things: one, serializability; two, recoverability. So in serializability we have four types. One is I will explain all the things in detail. Okay, because this is important. But first let me write down all the types so you get to understand about the thing. Meanwhile, if you want, you can pause the video and understand the each term. Okay, so first is conflict serializable. So what is conflict serializable? So if after interchanging the sequence of non-conflicting processes, we get a non-serial schedule, which is conflicting equivalent to serial schedule, then we say that the non-serial schedule is conflicting serializable. So I know the definition is quite difficult to understand, but let us understand it one by one. The schedules which are conflict equivalent to a serial schedule are called conflict serializable. So before understanding this, let us understand what is conflict equivalent. So I just wrote the definition of conflict and conflict equivalence for you. Okay. So what is a conflict? So two operations conflict if they belong to different transactions and they access same data item, and at least one of them is a write operation. So all these three conditions must satisfy. Okay, that is, there are two different transactions, they access the same data item and at least one of them is write operation, then conflict occurs. Okay, so let me show you here. So here, read, write, read, these both transactions are accessing the same data, that is A, and one of them is write. Okay, so this is the problem, this is a conflict. And what is a conflict equivalence? Two schedules are conflict equivalent if they involve the same set of transactions and the order of the conflicting operation is the same in both schedule. That means if you take conflicting pair and their order is identical in both schedule, then they are conflict equivalent. So let me try to make you understand this in simple terms. What we are doing right now is simply we are scheduling the operations. So two schedules are conflict equivalent if they involve the same set of transactions. So if T1 and T2 are conflicting, like here, T1 and T2 are conflicting, then conflict equivalence will always be between T1 and T2. Okay. The order of conflicting operation is same in both the schedule. That is, if here read, write, and abort, then in the final also there must be read, write, and abort continuously. Okay. The order must not change. If you take conflicting pair and their order is identical in both schedule, then they are conflicting equivalent. Now I think you will be able to understand what is conflict serializable, because what we are doing, we are studying conflict serializable. Okay, this was required for the conflict serializable definition. Let me write here. One, conflict serializable. So what I told you before, if after interchanging the sequence of non-conflicting processes, we get the non-serial schedule, which is conflicting equivalent to a serial schedule. Why serial schedule? Because we know that serial schedule is always equivalent. Then we say that that okay. So this is conflicting serializable. Okay, and this will also be consistent. This was the whole thing. Let me try to make you understand this with the help of a graph or a table. Okay, so this is the thing. The right one is a serial schedule and the left one is non-serial schedule. Okay, now for the trick part, like how will we understand that which one to swap and which one cannot we cannot swap. Let me give you a final table. Okay, okay, so as I wrote here, the below 6 diagrams will make us able to understand which process can be swapped without making it inconsistent. I can write this equal to this. Okay, this also equal to this. You can read it on yourself and understand it why it is equal using the example I gave you, method of taking a equals to 10, then reading and writing operation and all. Okay, so these are not equal. The 3 in right are not equal and the 3 in left are equal. I hope it is not so tough. So from this, what we can say that read operation is always non-conflicting and other operations will always be conflicting. Like read here, take a look at this. We wrote here WB. So these are different processes, but here RA, and here also RA, WA, whatever that. So only read operation are non-conflicting, otherwise all the three processes are conflicting. Okay. So what we can say till now that to end this conflicting thing, we can say that if one schedule can be converted to another schedule by swapping of non-conflicting instruction, then they are called conflict equivalent schedule. Okay, so I can write it here after these all. I hope you will be able to understand the conflict equivalent now. So if one, okay, so I hope this was easy for you to understand. Now the main part comes that what is the procedure of determining conflict serializability of serializability of a schedule. It can be simply done using graph. Okay. I guess I can underline this. Yes. Okay. So this can be simply done using graphs. This is nothing but a topological sort. We can write here also that the serializability of equivalent serial schedule the serializability order of transaction of a equivalent serial schedule can be determined using topological order of precedence graph. Okay. Now, but we also need to understand how will we create the graph. Okay. Like the serializability will be given by the topological order, but how will we create the graph for it? So there is some methods. Let me tell you the method. Okay, so I just wrote here the rule of making the precedence graph. Like how will you create the precedence graph? So precedence graph contains pair of G, like the vertex and edges. These are all just rule of making the graph. Ti executes right before Tj, then will have edge from Ti to Tj. Okay. Ti executes read before Tj executes write. I think I should write it like this. Okay. These are all just rules of making the precedence graph. That's all. You will need to remember it. Okay.